Okay, shall we get started? We've been seeing a lot of multiprocessing so far, but I want to cover the basics and give you some more perspective on some issues in multiprocessing. Clearly there's a lot to cover in multiprocessing, but we're going to cover what we can cover. Can you hear me in the back? John, is it good for the sound? It's good? Okay. Somehow I feel it's lower. It's better? Okay. Okay. So this first part may be a review, but hopefully it'll be an interesting review. Clearly we've covered heterogeneous multi-core, which is a form of multiprocessing. But we're going to be a bit broader in today's lecture. And probably we won't be able to cover everything in today's lecture, so we will talk about the rest in tomorrow's lecture. So this is what I intend to cover. Give you a basics of multiprocessors, and then we're going to cover some top issues like memory consistency and cache coherence. It's fun to look at these topics, but there's been a lot of effort spent on these two topics, especially in the 1990s, 2000s. They keep popping up in different ways right now. I want to give you examples of cache coherence. If you actually get rid of that, maybe that's not a good idea. Okay, these are some readings. These are all good readings, actually. If you have time, I would recommend going through these. These are overview readings, but this is, Amdahl's law, of course. I'm going to talk about this relatively old paper that defines different types of processing. And we're going to cover this one when we talk about memory consistency. It's only a 2-page paper. I'd recommend reading it. It's very high impact. And this is actually a beautiful paper that was written to introduce the Meze Protocol, which is the base of the cache coherence protocols in many processors. It's also called the Illinois Protocol because it was developed at the University of Illinois Urbana-Champaign. But we're going to go through that when we talk about cache coherence. But let's start with the basics of multiprocessing. If you want to talk about basics of multiprocessing, it's really talking about basics of parallel computing in the end. And this paper that was written by Mike Flynn in 1966 essentially set the stage in categorizing different types of computing. Basically, a lot of papers do this actually. They simplify, they abstract things. And his abstraction was basically, you have instructions and you have data. And instructions can be single or multiple. And data can be single and multiple. And you basically have to have these two orthogonal axes. You may have a system where a single instruction operates on a single element of data. Let's say a single element of data means single set of elements, let's say, because you do an add, for example, you add two numbers, right? That's considered a single element of data. That's the SysD. Or you can have an instruction that can operate on multiple elements of data. You specify the same operation on multiple sets of elements. And we've already seen that. That's SIMD, right? Single instruction, multiple data. Vector processors, array processors are examples of this. Of course, there's also the other side. You can have multiple instructions operating on a single element of data at the same time, single set of elements. This is a bit interesting. It's sometimes hard to envision, right? The closest form is really a systolic array processor, in my opinion. Basically, you have multiple processing elements operating on the same element of data, but the data gets transformed by one element before it moves to the other element. I cannot think of two processing elements operating on the same data element at the same time, perfectly concurrently at a given time. That's why it's a bit difficult to put machines into that category. We haven't covered systolic arrays in this class, but I would recommend looking into my digital design class from last semester, where we covered them in more depth. If we have time, we will get to systolic arrays also. It'll be a repeat of that lecture. But systolic arrays are essentially the basics of a lot of machine learning accelerators today. Essentially, we talked about when we talked about the Google TPU very briefly, but we didn't go into the details of it. Essentially, you have data input into processing elements, and then data goes into one processing element, and then that processing element does something to it, transforms it to something else, and then moves it to the next one, and the next one does something to that data, transforms it to something else, and then data moves to the next element. And the elements may be connected in a linear array, just like I described. They could be connected like a matrix, and they could have actually relatively irregular connections also. So you could actually design very specialized processors that take single data and transform it across stages to something else, and then output the data in the end. It's fascinating, I think. Clearly, they were developed before this, after this categorization came about, actually. The first historical case was in the late 1970s at CMU by H.T. Kuhn. Okay, and the last one is what we're going to talk about. What we have kind of been talking about, actually, a lot. But now we're going to talk about the processing side of it. But then we're going to transition quickly into memory. This is where you have multiple instructions, multiple independent instruction streams operating on multiple data elements. Right? That's MIMD. And clearly, this is one part of that 2x2 matrix that categorizes instruction and data into multiple and single. And clearly, there are multiple examples of it. We're going to talk about multiprocessors. But the multi-threaded processor is essentially a multiprocessor with very tight resource sharing in the end. You share the hardware resources. You have multiple hardware contexts. Maybe you don't have complete different processors, clearly, but you have a single processor that's shared by multiple thread contexts. Fundamentally, it's the same as multiprocessing. Right? That's the idea. Does that sound good? Okay. So now let's go into even more fundamentals. I would say this is a place where I'd like to get your input on also. So basically, the question always arises: why do we design parallel computers? Actually, if you go back over here, you can consider all of these as parallel computers. Clearly, this is very parallel. This data parallel, right? A single instruction operates on multiple data. This is very parallel. Multiple instructions are operating concurrently on different elements. This is also kind of parallel because you can actually input a wave of data. This, you could argue, is the least parallel of all of them. You have a single instruction stream. Each instruction operates in a single data element, but clearly we can parallelize this also, right? Out-of-order execution, for example, superscalar execution are examples of that. So parallelism is essentially doing multiple things at a time. It's applied to humans also, right? We operate on parallel if we do multiple things at a time. I'm moving my hands right now while I'm talking. That's parallelism. Hopefully there's some synchronization. I just don't move my hands randomly while I talk. So clearly I think you can apply a lot of these concepts to human behavior in the end. But what are things? Things could be instructions, operations, and tasks. And the granularity changes clearly with different types of parallelism. So I will give you the main goal, but I will ask you about what are potentially some other goals. So the main goal, or original goal in designing parallel computers is really this one. We want to improve performance. Execution time, and performance could be defined in multiple ways. You may have a single task which you want to execute much more quickly. You want to reduce the execution time as much as possible. And we talked about that in the last lectures, right? When we talked about bottleneck acceleration and heterogeneous multi-core. We said we have a single task, we write a multi-threaded application, and we want to reduce its execution time as much as possible. So we want to improve the parallelism. And we talk about the bottlenecks that we see when we actually increase the number of cores, for example. Or we may want to improve task throughput. We also talked about that when we talked about multi-program workloads, right? You may have programs that have nothing to do with each other, but you put them together on multiple processors or multiple thread contexts, and you improve the throughput that you get from all of those tasks. And these were goals originally to really design the systems. Today, cloud computing is a very good example for task throughput, for example. But in the past, batch simulations, jobs that people used to submit, cluster computing, for example, was an example of it. I mean, we already talked about execution time of a program being governed by Amdahl's law, and we're going to get back to Amdahl's law again over here. But clearly, this is not the only goal, actually. There are other goals. Can anybody guess what they are? I think there are 3 of them over here. And they're also fundamental. And I don't claim that these are comprehensive. Maybe there are other goals that we could add to the list. Different from the bottlenecks in the parallel portion. If you remember, there were 3 major bottlenecks in the parallel portion, and I claimed that they're very fundamental. And nobody so far has come up with something that we could add to that list. Here you may be able to come up with something that we could add to the list, because this is more of a goal-oriented thing, right? So why do we have parallel computers? Why do we want to have multiple? Let's say, why do we want to have multiple processors? Be more concrete. Our goal is not performance, let's say. What could be our other goal? People are still waking up, I guess. Yes?
The energy, if we have like specific processor or accelerator,
That's a good point. Basically, if you're saying energy can reduce with specialized processors, that's certainly true, and I agree. The first point is really related to energy, but What if you don't have specialized processors? I want to stamp out the same processor. You can still improve energy that way, right? Especially if you can parallelize your program. And that's a very good goal for parallel computing. Assume that you don't want to change performance. You can reduce power consumption or energy consumption also on top of this if you can parallelize your program nicely across n units. And this example over here says, let's assume that your base, you have a single machine and it gives you n units of performance at frequency f. What you can do is basically you can have 4 n units of performance. You can basically have 4 processors, let's say, and basically reduce their frequency. And if you can parallelize everything nicely, you will get the same performance, right? Does that make sense? So basically you divide the frequency by 4 of each. They're all slower processors, but because you can actually parallelize your computation really nicely, you're doing more things in parallel on slower processors, and as a result, you'll get less power consumption. So why? I guess that's the quick question, right? Because you're very clearly running at a lower frequency, right? And lower frequency enables you to run at low voltage also. And if you remember the dynamic power equation, it was correlated with basically dynamic power is some activity factor times capacitance times voltage square times frequency rate. Now what we're doing is we're dividing this by 4. This becomes f over 4. And actually voltage is correlated with frequency. So you can say voltage is like this, which means that voltage is being divided by 16 in this case, right? 4 squared. So you're really reducing your power consumption by 64, assuming you could do that. Does that make sense? Yes?
Why is voltage related?
Because if you want to speed something up, you really need to apply high voltage to it. That way you can operate the circuit at lower latencies. If you remember, I mean, my perfect example from the lecture is, if you remember when we were looking at the voltage latency trade-off in DRAM. And as you reduce the voltage, you start getting errors, right? You start getting errors because you're not giving enough time for the circuit to really share the charge in DRAM. So if you increase the latency, if you wait for longer, you will get correct operation. So that's one example. Intuitive. Yeah.
This is more related to capacity, no?
What do you mean capacity? Capacitance is this one. So that stays constant, basically. So you still, your power is really dependent on capacitance for sure. But that's hopefully not changing. Or that could also change actually, but I didn't incorporate it over there. That could of course change if you actually divide a single powerful unit to multiple smaller units, but that's not as easy to predict. Does that make sense? So basically the key takeaway is if you want to run the circuit faster, you really want to supply high voltage to it. If you want to run it slower, you can get away without high voltage. If you're really interested in details, you can take a microelectronics course. How many of you have taken a microelectronics design course? Okay, some people. So you've covered this hopefully in microelectronics. Okay, I would recommend that. Okay, but does this make sense? But of course, this assumes something, right? This assumes that you are perfectly parallelizing your program. Again, your time doesn't change. If your time changes, then you may not be able to do this, because you may not be able to get the same performance, right? In the end, your energy consumption may actually increase, and your average power consumption may also increase. But your peak power you can reduce it this way for sure. But peak power may not translate to energy in the end. It may not translate to average power, which is also energy, if you don't parallelize things well. Does that make sense? Okay. Any questions? People agree with this, right? This was actually the motivation for multi-core also, right? People said, oh, we have these huge, powerful processors. They're complex, they're power hungry, they're doing one thing at a time, meaning one task at a time. Ignore multi-threading, of course. And we're running them at high frequency. Wouldn't it be nice if we actually had a much simpler core in order core and stamped them out, we could run them at low frequency and get a much better power consumption, much lower complexity also at the same time. And in the end, we could hopefully get the same performance as well if we could parallelize things. But of course, you know that doesn't work out very well all the time. So if your application is completely parallel, this is a very good trade-off. Or if it's close to completely parallel, it's also a very good trade-off, right? But if you have a lot of bottlenecks in your workload, this may not improve your energy consumption significantly in the end. You may actually reduce your energy consumption, increase your energy consumption, because your task is running much slower now. Okay, so this is only one of them. What else? Yes? That's good, yeah?
How the core fails to work or actually provide different results, maybe you can compare.
Exactly. Basically, you can have redundancy in the cores, and if, let's assume that you have the same task, and it's important to you, you execute them on n different cores, and you basically vote on the results. That's the idea. And yes? So that is true actually. If you reduce your thermal maximum power, you certainly reduce your heat because the heating becomes slower, and yeah, so it has positive effects on thermals also in this case. I didn't include that over here. We keep including this over here. That's why I said it's not a comprehensive list. But those are all function of the power consumption in the end. But what your colleague said, the reliability is one of the points over here. Unfortunately, it's the third point. So I'll put that later up. But essentially, it's called n-modular redundancy, right? You have n processors, they're all doing the same thing, and you compare the results. And as n grows, of course, your tolerance to faults increases. But of course, your cost also increases for redundancy. And that was actually one of the early uses for parallel computing for redundancy. Like tandem computer in late 1970s. They were designing these computers, multiprocessors that were used in critical applications, either safety critical or sometimes they sold a lot into banks, for example. And one of the major innovations was essentially having dual modular redundancy. They have two processors, and they would run the same application in lockstep in both processors. Lockstep meaning that both of the processors need to agree on the result of an instruction before you could actually finish the instruction. And if they both agreed, everything is good. Now, if they didn't agree, what happened was clearly you don't know. You know that there's something wrong, for sure. But you don't know what went wrong. You cannot vote. Well, you can vote, basically, it's 50-50, right? So you don't know which processor is correct. So their major, one of their, this is a practical thing, but they had an LED on the board, which basically turned red when the computers didn't agree. Now, actually, if people were operating the cluster at that time, they could go and figure out easily which computer was not doing the right thing, and they could replace that computer. So that red LED is very important. That's the user interface for dependability in the end, right? If you didn't have that, it's very hard, of course, to replace. But yeah, that was the third. That's the third thing over here. So there's another. Yes.
It's scalable.
Okay, that's good. I like that. Why is it scalable?
You can have in your phone 4 units, in a computer 16 units, and in your server 100 units.
Okay. You mean parallel computing is scalable?
Yeah, so you can have the design for the smartphone is the same as for.
I see. You have a different thing than what I have over here. But yes, it could be true, basically. You design the same core and you basically replicate it for scalability. Maybe a different way of thinking it. Maybe it's related to this, but essentially you can improve cost efficiency and scalability and reduce complexity by having parallel computers. And this has relations to this one also. But basically it's harder to design a single unit that performs as well as n simpler units. Again, the assumption is that you can parallelize your computation. Right? And also, or your computation is already completely parallel. Does that make sense? Yeah, and this was also the motivation for multi-core as well. Right? And the third one is we discussed there, the improved dependability. Okay. I mean, this is also, this of course, assuming that we do parallel computing in time, right? In space, meaning that we add more computers. You can always think about improving all of this in time as well, meaning you can do parallelism in time. For example, if you want to actually improve dependability, you can also do redundant execution in space, in time. Meaning you have a single processor, and you basically execute the program, and execute another copy of the program, and before you actually report the results to software, you make sure that the programs match. But of course, that's not parallel computation anymore. That's something else. So parallel computing enables you to space to do these things faster. Okay, so clearly there are different types of parallelism also. There's instruction level parallelism, which we talked about. Different instructions within a stream can be executed in parallel, and actually digital circuits, digital design lectures cover a lot of these. Pipelining, automated execution, speculative execution, VLIW, data flow. It's fascinating, I think. They're all parallelism. Very nice. But we're not going to talk about this as much. Data parallelism, we talked about that with the SIMD processors, vector processing and array processing, GPUs. Essentially, different pieces of data can be operated on parallel, and systolic arrays and streaming processors also exploit some sort of data parallelism in the end. And the third one is really task level parallelism. Essentially, different tasks and threads can be executed in parallel, and this is what really multi-threading and multiprocessing is about in the end. Clearly, you can combine all of these different types of parallelism, and existing processors combine all of them, right? You have a multi-core processor that has a SIMD unit, that, and each processor actually employs a lot of these techniques over here. Okay, so but let's talk about task parallelism. So clearly, creating tasks is important for getting tasks to be executed in parallel. You can partition a single problem into multiple related tasks or threads. These are essentially cooperating tasks. They're all cooperating to solve a single problem. And the other ones, tasks are given to you, hopefully, by other people, and you run many of these independent tasks together, right? This is easier, of course. Well, whereas this one's hard. You can do this explicitly. So clearly, how do you create the tasks? You can create the tasks explicitly as the programmer or the compiler. Basically, some sort of thing that's that takes the problem and partitions the algorithm into multiple tasks. And this is easy when the tasks are natural in the problem, clearly, right? Like some queries, maybe natural. But this is difficult when the natural task boundaries are not clear. And that becomes a problem when you actually are doing parallel programming. And we've kind of seen that in the bottleneck exploration part. You could also do this implicitly, actually, which is also interesting, I think. Basically, you can take a task or a program, let's say, that's written for execution on a single processor, single thread, and it can create these tasks implicitly. Meaning you can divide this single thread into multiple threads somehow, partition a single thread in some way. This turns out it's not very easy to do. There's a lot of work, actually. There's a lot of research in this area. It's called thread level speculation. Essentially, partition a single thread speculatively. For example, if you may have a single loop with many iterations, right? A billion iterations, let's say. You can speculatively say these iterations are independent of each other without having any knowledge that was provided to you by the programmer, because the programmer gave you a single-threaded program. And the hardware, or the system plus hardware underneath, can say, okay, I'm going to take iteration 1 through 10 and execute on this core. Iteration 11 through 20, execute on this core, ... And if they're really independent, now I can actually finish what I've done, right? Meaning that I can commit the results of each of those tasks that I created dynamically. But of course, this requires answering the question if they're really independent or not. Which means that this requires some additional overhead to check whether the implicit partitioning of the tasks that was done by the system and the hardware, you could do it in software, actually, purely in software. You could do it purely in hardware. You could do hardware and software cooperatively, and you could imagine mechanisms for doing that. There are a lot of creative ideas in this direction. But you really need to do it, and that actually adds a lot of overhead into the system in the end. But people have shown that this could be beneficial, but it's not as good as a programmer going and partitioning the tasks themselves in a clear way. So again, it's an example, another example of the programmer microarchitect trade-off, right? Does the programmer go and put the effort into partitioning their program into tasks? You get a lot higher performance that way, because you know, and if a programmer says these tasks are independent, it's their responsibility, right? Or do you actually do it automatically, transparently to the programmer, in which case the programmer does nothing, but now the architect has to do a lot. And it turns out the benefits over here are usually smaller. And even though there's been a lot of research, like decades and decades of research over here, not a lot of it went to real products actually in the end. I guess the closest thing that has went to products is transactional memory, which essentially you can specify transactions, but even that requires programmer support. Basically, the programmer says, okay, this is a transaction begin and this is a transaction end. And those transactions can be executed in parallel by the hardware. And again, hardware does the conflict checking. Okay, so any questions? Okay, and the next one is, of course, hopefully simpler, where you already have many processes that are given to you. Cloud computing is a great example of this, right? You collect processes from everyone in the world, you run them on your machines, they're clearly independent, because they're from independent people. And in this case, the goal is really to maximize the throughput, if your goal is performance over here. And this is easy when there are many processes that are already given to you, as we discussed. But of course, this is a bit easier because it's really the goal is not to improve the performance of a single task in this case. Okay. But clearly, multiprocessors are used for this purpose also. Multiprocessors, multi-core, multi-thread processors. It's used for that purpose, and they're very successful actually on that front. All of these cloud computing companies are doing extremely well, right? Actually, they're doing extremely well because they're taking away the burden of management of a lot of infrastructure from people in the world, right? But of course, they're creating a lot of privacy issues also. If you're really willing to give your execution data and everything to some random company, then you get rid of the burden of managing your own systems, clearly. Okay, but that's a different issue. So let's talk a little bit more about multiprocessor types. I'm going to give you an overview of multiprocessing. Clearly, there are multiple ways of approaching designing multiprocessors. One is coupling them loosely, and the other is coupling them tightly. And we've seen examples of this. Loosely coupled essentially means that there is no shared global memory address space across processors. This processor has its own memory address space. It cannot access the memory address space of another core, let's say. You can think of this as a multi-computer network, actually. A multi-computer network is this, essentially. Tightly coupled means there is shared global memory address space, so whenever I do a load to a memory location, another processor can also see that memory location. And another processor can do a load, another processor can do a store. So essentially, we share all the memory locations. Clearly, there's a design space between these two. You can combine somewhat part of the processors that if you have a big multiprocessor system, some of them may share global memory address space, and some of them may share their own global memory address space. And between these clusters or different partitions of the multiprocessor, let's say you don't have a global shared memory address space. You could have a heterogeneity in these models also. But in the extreme, these are loosely coupled multiprocessors, and as I said, these are multi-computer networks. This computer and that computer over there are not sharing a global memory address space, clearly, but they can communicate with each other. So how do they communicate with each other? Well, before that, this is more traditional multiprocessing. It's called symmetric multiprocessing. And existing multi-core processors and multi-thread processors are like this. Although it's good to re-examine some of the approaches, clearly, to think about maybe there's some benefits to this also. So usually these, if you really want to partition a single task across a multi-computer network or a loosely coupled multiprocessor, then you program using message passing. Essentially, if you want to, this task is executing over here, and the cooperating task is executing on some other computer. The way you communicate it is by saying sending and receiving data. This is message passing, and we've seen this in the Tesseract paper, for example. That's an example, right? Clearly, it has benefits for communication because now you have completely different address spaces, and you got rid of part of the coherence problem, clearly, as we will discuss later on. Okay, whereas here, but the programming model is different, right? Now you cannot just, it's different from a single-threaded programming model, I should say. If you're coming from, if your blank slate starts with message passing, then clearly that's a good programming model for you, right? But if you start programming a single-threaded processor, then you get used to having loads and stores to arbitrary locations in memory, And it becomes maybe more natural to think about if you have another processor, oh, okay, it also has access to all of that memory. That's why I think this programming model is more intuitive for people who are very used to single-threaded programming. Except, of course, when different processors need to operate on shared data or shared memory locations, they may require synchronization, especially if they need to do it at the same time, right? Or close to the same time. So that's different. So here, there needs to be some synchronization. Here, the synchronization is a lot more explicit, right? Whenever you want somebody else to operate on some other data, you send. But here, it's more implicit. Somebody else can load a memory location, right? Or somebody else actually can store to a memory location that is visible to all of the other processors. So this could potentially be more prone to bugs also, actually, in terms of, for example, stray pointers. Right? You store to a memory location, you somehow calculate the wrong address, and you may actually corrupt the memory space for some other task because it's globally shared memory. Whereas here, the damage is kind of limited, if you think about it that way, because you may corrupt your own space as long as you don't send it to someone else. That's fine, right? You cannot just have a stray pointer that corrupts somebody else's space because without sending it. You have to do a lot more to actually corrupt somebody else's memory space in this case. Does that make sense? Okay. But these are clearly good models for communication. As I said, there could be things in between. And people have designed multiprocessors in both ways. So if you had actually more time, I would talk about different things, but I'm not going to go into this. If you actually have a parallel computing course, these could be the design, hardware design. Hardware itself can actually have shared memory like this, or hardware itself cannot have shared memory. But there's also the programming model, which is completely different. Programming model can have shared memory or not have shared memory, but the underlying hardware can be completely opposite in the end. Does that make sense? So there's a distinction between programming model and the hardware design. Clearly, if the programming model matches the hardware design, that could be good, right? If you already have send and receive calls in your hardware, then your programming model can be directly mapped to those send and receive calls. And actually, people have proposed mechanisms to have coherence at the programming model level on a hardware that doesn't provide that coherence, on a multi-computer network. For example, you can actually have coherence across a multi-computer network with a system software layer that actually enables that coherence. Make sense? Meaning you have a global memory address space, basically. And in the programming model, you have the global memory address space. You program assuming that you can do a load, and that load is visible to all of the processors, and store is visible to all of the processors. But the underlying hardware is really a multi-computer network. And in the end, there's some middleware, let's say, that translates your software, your loads and stores to network calls. You can easily imagine that. Clearly, there's a lot of overhead in this. You probably don't want to do it, but you could design a multi-computer network. Well, why would you do it, I guess? Why would you do something like this? I could imagine some cases where you may want to do something like this. Your underlying hardware multiprocessor is really a multi-computer network, but your programming model is global memory address space. Any guesses? Yes?
Multiprocessing hardware, you have access to more nodes. Mm-hmm. In general, especially cloud computing.
Yeah.
And on the other hand, if your programming model is shared memory, then you can actually enhance the speed of the individual tasks that we discussed. Mm-hmm. So maybe this will be combining the best of both worlds. You have the most hardware, and also you get the most performance by combining tasks. Yeah,
that's a good way of putting it. I will rephrase that. With the hardware, you can actually are much more scalable probably with a multi-computer network. And also, I mean, it's freely available, right? You can put together many computers without really designing a specialized shared memory multiprocessor, right? It's a lot easier to do it on. It's already there, right? The multi-computer network is the internet. And as you said, the programming model over here maybe more intuitive to use, right? That's what I would suggest actually. If you have global shared memory address space, maybe you can more easily optimize your program because you're used to it. And some programs actually may, this is actually harder to claim of course, but this is always a good, there's always a camp that who are proponents of message passing, and there's another camp who are proponents of shared memory. So there's no reason to get into this religious argument. But clearly I can imagine some cases where if your application is really operating on tightly coupled data, you may actually want to have a shared global memory address space and just update that location, right? As opposed to sending and receiving and preparing messages. It could be lower overhead at the programming level. And it could be more intuitive, it could be easier to program depending on what your application is and who your programmers are. As a result, you may actually want to go to that solution. So it's not an unreasonable solution in the end. In the end, it really depends on your requirements. So it's also possible. But this is to demonstrate that you can have a hardware model that's loosely coupled, whereas a software model that's tightly coupled. And I think all combinations are actually possible. But we're not going to go into it. Okay, any questions? Spend a lot of time on this slide. Okay. So it's clear there are a lot of design issues in tightly coupled. We're not going to talk about the loosely coupled multiprocessors more. Actually, we've been talking about tightly coupled multiprocessors a lot when we talk about bottleneck acceleration, for example. And we're going to talk more about tightly coupled multiprocessors because there's some really interesting design issues over here. One is synchronization, and we'll be talking about that. You already are familiar with that. We're going to talk more about cache coherence. Basically, these are going to be about how to ensure correct operation. Essentially, how do you ensure correct operation in the presence of caches that are in different processors and they keep the same memory address cached? How do you ensure that the updates do not conflict with each other and processors get the correct data? And the second one we're going to talk about is about memory ordering. What should the programmer expect the hardware provides in terms of the ordering of operations? And you will see that if the hardware doesn't provide any support beyond a single processor, then you may actually run into incorrect operation, especially when you're implementing synchronization primitives. And clearly we talked a lot about shared resource management. I mean, tightly coupled multiprocessors have this problem. And we're going to talk about interconnects because in the end, if you want to scale a tightly coupled or loosely coupled multiprocessor, you still, you're bottlenecked by your communication substrate. So we'll talk about interconnects later on. So these are design issues, but there are also programming issues related to this, and we talked about this as well, so I'll go through this relatively quickly. But clearly, when you're programming, you want to distribute the tasks, and the load on each processor becomes important. And as we discussed in the last couple of lectures, it's usually hard to partition a single task into multiple tasks while keeping the load balance. As a result, you have these lagging threads in the end, or lagging cores. Clearly, synchronization is important. How do you synchronize efficiently? How do you communicate between tasks? And what kind of primitives do you expose to the programmer? How do you optimize all of these? We're not going to talk about the software side of it, but there is a lot of work also on optimizing the synchronization primitives, clearly. Contention we talked about. How do you maximize parallelism? I mean, these are kind of related to this also. And we're going to talk about ensuring correct operation while optimizing for performance. As we said, there's always a trade-off between performance and correctness, or performance and effort. And it's very difficult to get rid of that trade-off. Okay, so I'll give this aside. We're not going to talk a lot about multi-threading in this class, since we don't have enough lectures, but hardware-based multi-threading is a special form of multiprocessing. You have multiple thread contexts, but this also has a design space. Existing processors, for example, can do simultaneous multi-threading, which is the finest grain form of multi-threading. But you can be very coarse-grained, meaning you can have multiple thread contexts in a single core, let's say, and you can switch between the thread contexts relatively quickly, but you don't concurrently execute from those thread contexts. You're executing from one context, and if that context, for example, based on an event, you yield to the other context, and another context starts executing. For example, if a thread that's executing gets a long latency cache miss, you can switch to another thread that's already on the processor, right? And you, of course, need to have the resources to switch to that thread relatively quickly, meaning a separate register file, a separate program counter, a separate machine-specific registers to handle the virtual memory and all of that. But of course, you don't need to have both threads to be active at the same time, which means that the requirements on the amount of registers that you need to access is much lower than the finest grain form. In CPUs, in GPUs, we talk about fine-grained multi-threading. It's not the finest grain form of multi-threading. Basically, we said that every cycle you switch to another thread. That enables you to execute from multiple threads concurrently, clearly, and that requires, of course, you to be able to access access the registers of every single thread that you have in the machine, and that provides you high performance clearly. But that doesn't help with the single thread performance. Here you get good single thread performance, and when your thread stalls for some reason, you switch to some other thread. Right? Or you could do this quantum based. Actually, there are a lot of interesting policies over here. For example, Intel Itanium switched to an L3 and they have a very good explanation of how they did it in a paper that was written in 2005. Clearly, this is also old. It was first employed in the CDC 600. But the most fine-grained form is really simultaneous multi-threading. Essentially, here, for example, you're really fetching from a different thread in every cycle. Here, you can actually fetch from multiple threads in a given cycle. That's the most simultaneous multi-thread. Here, your instruction scheduler can pick from different threads in a given cycle. Basically, in the same cycle, you can pick instructions to execute from different threads. If you have enough functional units, you can utilize all of your functional units this way. Whereas in fine-grained multi-threading, if a thread, you fetch from one thread, and that thread needs to utilize all of the functional units, right? If it doesn't utilize all of the functional units, then you're really wasting some functional units. With simultaneous multi-threading, you can actually pack the threads instructions nicely such that you don't waste functional unit utilization. That's the idea. A lot of actually existing general purpose processors are simultaneously multi-threaded. Intel calls this hyper-threading, still I think. I kind of don't like that hyper-threading thing, but it's essentially simultaneous multi-threading, simultaneous fetching and execution. And there are clearly a lot of design choices that go into all of these. So the upside of simultaneous multi-threading is you get the benefits of high throughput, but also you hopefully get the benefits of high performance in a single thread, right? Because you're really not switching cycle by cycle. Here, in the purest form of actually the definition of fine-grained multi-threading is you fetch from one thread every cycle, and if you have, let's say, n threads, the next time you fetch from the same thread is n cycles later, because you really need to fetch from the other n-1 threads in the remaining n-1 cycles. Make sense? Here, you can actually fetch from all the threads at the same time. Of course, in real implementations, fetching from all the threads at the same time is not easy. So real implementation of simultaneous multi-threading fetch from one thread, but there's a lot of delays that happen in the back end of the pipeline. As a result, there's a lot of buffering that happens. So even though you may fetch from one thread, there's backup in the pipeline, you can still execute from multiple threads concurrently. You can pick multiple threads instructions to utilize your functional units because there's a lot of backup, right? Okay. Any questions? Well, that's my one slide tweet of multi-threading, hardware multi-threading. Doesn't do justice to the concept, but hopefully it gives you the basic ideas. Okay. So we'll spend a little bit more time on limits of parallel speedup because I think there are some important things to discuss here. Although you've seen some of this, so I'm going to go through some of this relatively fast. I'm going to give you a puzzle. Ready? You may want to take out things that you want to write on. But basically, we're going to look at this example. It's a simple example, right? This is a polynomial, and this is some constant times x to the fourth power plus some other constant times x to the third power plus some other constant times x to the second power plus some other constant times x plus a constant. Right? So we're going to evaluate this. And assume that we have given inputs, x, a single value, and each constant that you have over here, constants a, ai. And assume that each operation takes one cycle. In this case, we have only multiplication and additions, right? Addition takes one cycle, multiplication takes one cycle. There's no communication cost between processors, which is really very optimistic, as you can see. And each operation can be executed in a different processor. And each processor is capable of executing them a single multiplication or a single addition at a given time. Now the question is, how fast can you execute this with a single processor with these assumptions? Of course, assuming no pipeline or concurrent execution. Basically, in a given cycle, you can just do an addition and a multiplication. In the next cycle, you can do an addition or multiplication. Make sense? And then I'll ask you, how fast is this with 3 processors? I shouldn't go to the next slide. Be careful. And then I'll ask you, how fast is it with 3 processors? And then we're going to compute the parallel speedup, basically. Parallel speedup is basically, well, hopefully this is faster with 3 processors. And how fast is it with 3 processors compared to in a single processor? I'll give you some time to give me some numbers, I guess. You can actually calculate it in your head also. You may not need the thing, but it helps. Should I wait more? This is a fun question. One more minute. I'm going to take a vote on the answers to both of these questions. Hopefully you get some parallel speed up. Okay. Any answers? So how fast is this with a single processor? Go ahead. Yes?
On the speculation, you can do it in 8 cycles.
8 cycles. That's a good answer. Anybody else? Do you agree, or can you do better? Or maybe you say your colleague optimized the program too much and it's wrong. That's also possible, yes?
I have a question.
Yeah.
So A1 times X is one multiplication.
Yes, yes, it's just...
But A2 times X squared would be 2.
Absolutely, yeah. A2 times X times X.
But for something like X to the 4th, could you simplify that into like A4 times X? No, X times X to X squared, and that times the multiplication itself.
Yeah, absolutely. Which is Horner's factorization that your colleague mentioned, right? No other takers? Everybody's fine with 8 and it's correct? Now if you want to be even more correct, you can do it in 11 cycles. This is the simplest thing that you can do, right? Basically, do this over here. Well, maybe you were doing this, I don't know. But you didn't give me a number. But basically, you draw the data flow graph of what you have over here. This is A1x. Here you compute the x squared, x cubed, x to the 4th over here. And then you feed it to the appropriate places. And then you have the reduction, let's say, addition 3 over here. And it's not bad. It's 11 cycles. So maybe you're wrong. Just thinking right now. You're actually right. but that's we'll make the point. But this is the algorithm that you could come up with without thinking much, perhaps, right? And it takes 11 cycles. That sounds good. Okay, we'll revisit the 8 cycles later on, maybe. What about the answer to the second question? How fast is it with 3 processors? Anybody? You're the TA for the course. Do you want to answer? If TA is the only one answering, then that's not good. Although I'm curious if he's correct or not correct. Yes, please.
5 cycles.
5 cycles, okay. How did you come up with it?
One processor will just calculate, multiply x
Mm-hmm.
in every cycle, and the other one will just take that value and multiply with the constant.
Okay.
And the third one will add them.
Okay, that's one way of doing it, sure. Anybody else? 4 cycles. Okay, how would you do that?
The first cycle is A3 multiplied by x and x squared and A1 squared. A1x, and second cycle is A3 something.
Okay, anyway, maybe we can look at that later. I think you're too aggressive. If you can really do it in 4 cycles, then I'd like to change my solution later. Yes?
I think it's hard because if you look at the depth of the actual data flow graph, and the bottleneck curve is A4 times x.
Exactly, yeah. I think, yeah, exactly. A4 times to the x to the 4. So I think you may be either assuming there are more resources than there are, or not taking into account one of the computations. That's my guess. Okay. So who thinks that it's 4 cycles versus 5 cycles, now that I biased you? The question is, how long does it take? 5 cycles? Who says 5 cycles? Who says 4 cycles? You say 4 cycles. Okay, the TA agrees with you, so you guys need to talk maybe. So I'm happy to change my slide if I'm wrong. Who says more? Even 5 is wrong. Okay, nobody says. So okay, let's go back to the. So you said 8 cycles for the single processor version. What is your answer for the 3 processor version?
Right?
Yes.
I was 6, but I didn't.
I see. He didn't optimize it well. See, you can see we get different answers even with a simple problem like this. That's the difficulty of parallel programming in the end, or assumptions actually. You may actually violate some of the assumptions. So this is what I get basically. This is 5 cycles. We have 3 processors. And each of them can do 1 operation in a given cycle. There's no communication cost, which is magic, which is also a huge assumption clearly. But this is the critical path basically, like you mentioned. It's a to the 4 to the x to the 4, a4 to the x4, right? And then there's also this plus. What do you think? You missed the last part. Okay, there you go. What about the TA? You also missed the last part. So essentially, you optimize your program too much that it was incorrect now. Which is essentially that trade-off that I was talking about, right? Performance versus correctness. Even a very simple program like this, that happens. If you spend enough effort, enough time, you will figure that out, and you will fix it, and you will come up with this solution, or maybe a more conservative solution, right? But this is, I think, the fastest you can do, which is 5 cycles in this case. Okay, so now you can go and compute the speed up with 3 processors. Even with the assumptions that we made, no communication cost, the 3 processors take 5 cycles, and a single processor takes 11 cycles, and we get 2.2x speed up. Even with all those assumptions, it's still not 3x speed up, right, on this, because there are dependencies that you have in the computation. Now the question is this a fair comparison? Assume that our assumptions are correct. I'm not questioning the assumptions. Assuming all that is correct, is this fair? Yes?
Well, if you take a look at download law, it maybe misrepresents the fact that maybe this represents the fact we didn't parallelize well enough.
Okay.
If you look at download law, it's actually, you can see that we see bottlenecks by the sequential bottlenecks.
Yes, that's.
So it can be fair in a sense if we are aware of the fact that sequential thing might not be able to parallelize completely.
Yeah, okay. That's true. From that perspective, it's fair.
It's not fair to compare maybe different solutions in this way because they don't take a look at the sequential part versus the parallelizable part. Maybe in that sense it's not fair to just look at the speed up like this.
No, I think in the end it's fair, right? You basically have a single processor and you're dividing its execution time with multiple processor execution time. But of course, while you're doing that, you need to be a bit careful. We established, hopefully, that 5 cycles is the best you can do in the multiple processor case. But did we establish that 11 cycles is the best you can do in the single processor case? I guess not, because your colleague mentioned that he could do it in 8 cycles. Assuming he is correct, then this is not fair, right? Because you're not comparing the best algorithm that you could design for the single processor with the best algorithm that you could design for the multiprocessor. And he mentioned Horner's factorization, which is exactly what you should do, actually, if you're designing a single threaded algorithm. And you probably learned about Horner's method. It was published in this nice paper in 1819. You can read it. I'm not going to assign it. But this is essentially a very well-known method for polynomial factorization, right? And essentially, this is what you do. And you can actually have a nice table to do this. That's what I used to do in my, I guess as early as grade school, right? Whatever you call it, primary school, yes. But basically, that's what it is, right? You factor out x, and you keep factoring out x, and that's how you can minimize the number of computations that you do over here. If you do this, this is what you get. This is much better than 11. This is really 8. And if you can beat this, then you're probably doing something wrong. You're over-optimizing your single-thread program, maybe ignoring the last operation over here. But this is essentially what you get. And if you do this, it's 8 cycles. And now your speed up is even lower with 3 processors. Assuming that this is the best algorithm, 8 cycles, and the 3 processor algorithm that we talked about is also the best algorithm. 8 divided by 5 is 1.6. So now your 3 processor is not giving you even close to 2x performance. And we're still assuming that there is no communication penalty. Okay, so basically, that's not a fair comparison. Because if you really want to do the fair comparison, you should really use the best known algorithm for each of the different systems. That's the takeaway over here. Now, of course, it may not be the best algorithm, right? Because somebody may come up with a better algorithm later on. You don't know that, but you should really do your best effort to use the best known algorithm. Okay, so if you basically, if you're not fair, you can actually get into superlinear speedup that we talked about in earlier lectures. Basically, you keep adding processors, and your speedup becomes superlinear. In this case, it didn't clearly, but speedup was larger than what it should really be if you use the best algorithm. typically what you get is something like this, and you've seen a lot of these curves in the last lecture, right? Usually, actually, if you keep adding processors, things become going down because in real systems you have communication that happens between caches, for example. But if you're getting linear speed up, that's great. Now, if you're getting super linear speed up, there are really two potential reasons. And if you come up with another reason, let me know. I think it's going to be hard to come up with another reason. One is really unfair comparisons, meaning you're probably not finding the best best serial algorithm, or best algorithm for any point over here for different processes. You're comparing some parallel algorithm that's better than the serial algorithm, and that's essentially unfair. Or you're adding more resources, basically. We talked about this also. I mean, sometimes in real life, when you actually add processors, you get really super linear speed up. And that's real when you do the measurements. It's not because of unfair comparison, because you really found the best known algorithm. But the reason is you may have cache memory effects. Because when you add more processors, you're not just adding more computation power, which is what the previous example was about, but you're also adding more cache, or memory, or both at the same time. And once you do that, what might be happening is, across the multiple processors, you're going to memory much fewer times compared to the single processor. Your memory bottleneck is going away, basically, or reducing, if you will. Because now you have a lot more resources in your cache. So for example, my favorite example over here is, you have one processor with, let's say, 1 megabyte cache. Your working set with a single threaded, or your working set is 2 megabytes. Now if you actually parallelize your program and run it on 2 processors, and if you add 1 more megabyte of cache, because each processor has 1 megabyte cache, now your working set ends up fitting into 2 caches of 2 processors. So technically you don't go to memory. Whereas a single processor is always going to memory because it keeps trashing the cache. Clearly you will get a super linear speed up if that's the case, assuming your parallelization, everything also works out, right? And that's because of the cache and memory effect. Make sense? So of course, now it becomes harder to do the pair comparison if you're adding more of these resources, right? How do you do the comparison? You have a single processor, 1 megabyte cache. Maybe you add another processor and halve each of the caches. Then you actually have the same cache effect, and don't change the memory bandwidth, don't change the memory. Maybe it's good if you really want to look at the scalability of your algorithm, but if you're designing a real system, that may not be really what you want to do, right? Okay, so you should be cognizant of this basically. If you get a speed up curve, it's always good to understand where the benefits are coming from. And if you definitely get a super linear speed up curve, you should always question why. It could be this, it could be this, it could be a combination of both of these. And then it becomes worse actually, because if it's a combination of both of these, okay, you're getting these effects for real maybe, fine, because the system is going to be designed that way. But you're getting some effects that are not real, meaning that somebody else can come up with an algorithm that's single-threaded that could actually invalidate a lot of your results, right? And that somebody else could be a competitor in a company, right? Oh, you designed this sophisticated multiprocessor that is accelerating something by 10,000x. That's your claim with 200 processors. And somebody else says, okay, I have the serial algorithm, and your results are only 200x actually. Or something like that, right? This actually happened recently with some quantum computing work that was published, if you're aware of that, right? Some company claimed that they were getting 10,000x or so in some algorithm, than some other company, you can read it online, said that, oh, there's a much better algorithm if you actually, for a smaller set of processors, and your results are actually invalid. Okay, I'm not going to talk about the companies, you can find out. There's a lot of hype in that area, so. Okay, so it's very fundamental in the end, because of whatever substrate you're using. Quantum computing, not quantum computing. If you don't choose your algorithm carefully, you may get these super linear or unfair comparisons. Okay, let's talk about some metrics before we take a break. This is going to be simple, but they're actually important. Important to understand in a fundamental way how multiprocessors are evaluated. So there are some traditional metrics to understand multiprocessors, and they're called utilization, redundancy, and efficiency. So traditional metrics assume that all P processors you're parallelizing the program across P processors, and all of the processors are tied up for the parallel computation for the entire duration of the parallel computation. You can, of course, optimize this. Right? So utilization is essentially how much processing capability is used. It's also a number of operations in the parallel version divided by number of processors times time the processors are tied up for. We'll give an example of this. So redundancy is how much extra work is done with parallel processing. This is actually interesting because whenever you want to do parallel processing, you actually are doing extra work. So what does this mean? Basically, this is the number of operations in the parallel version divided by number of operations in the best single processor algorithm version. And in the parallel version, you actually are doing extra work because you may need to, for example, replicate the data. You may need to do more communication. If you keep adding those, actually your redundancy increases and increases. Ideally, if you want to optimize a program, you want to minimize your redundancy. So you want to do the same amount of work, but that's usually not easy, right? For example, if you think intuitively, let's say I'm going to count the characters in this 1,000-page book. Yes, the work that you're doing in terms of counting each page is perhaps the same in a single-thread version versus n-threaded version, but now you have to distribute the tasks in a parallel program. So how do you distribute the tasks? And then you have to do the reduction in the end, add the histograms together, and that requires more communication. So that's extra work. So you add extra work for setup, you add extra work for result collection, and you may need to add extra work to parallelize your program because this part of the program, this task over here, may need some data. This task over here may also need some other data, and there might be some shared data that they both need. But they're not going to update that shared data, let's say, in the simple case. They're just going to read from that shared data. It may make a lot more sense to actually replicate that shared data in both processors' memories. And that adds additional redundancy. This is also very fundamental. As you keep parallelizing your program, your redundancy increases. And the last one is efficiency, which is an important metric, clearly. Basically, this is the time it takes with one processor divided by time it takes with P processors times the number of processors. And efficiency is actually utilization divided by redundancy. If you actually do the calculation, if you followed all of this, you'll find that out. But let's take a look at the example that we've seen earlier, the simple polynomial evaluation example. This is essentially utilization is how much processing capability we use. Recall, actually, or trust me that this was the case. Basically, we had 10 operations in the parallel version. They took 5 time units. Essentially, utilization means that we have 10 operations and we tie up 15 operation slots. Basically, this is it. We're utilizing 10 of the operation slots of 15 that's available to us. Make sense? It's operations with P processors divided by P times D. Yeah, anyway, you can do this on your own. So that's our utilization. Redundancy, I mean, this is very easy to calculate based on the graphs that I showed you. Essentially, operations with P processors, even without the communication cost, we had 10 operations actually with 3 processors. Whereas with the best single processor algorithm, Horner's method, you get only 8 operations. So the parallel version has actually more operations than the single thread version. And R is always greater than or equal to 1, as I mentioned earlier. And your goal should be really reducing R, but again, that doesn't mean that it's performance. Because sometimes you may want to do more operations because that enables faster access to data from your different tasks that are executing on different processors. So this is definitely not the only metric, but it's good to understand this metric. And efficiency essentially is how much resource we use in the parallel computer compared to how much resource we can really get away with. So basically, if you look at this, it says we're basically tying up one processor for this time units, divided by, we're tying up P processors for TP time units. And in the end, you get 8 divided by 15. So you could have used 8, but we're really using 18. We're really using 15. So our efficiency is actually very low. Well, more than half. So of course you could say you really don't need to tie up these slots over here, but then you need to do something smarter, right? You need to know when this particular task is done, and then you deallocate it, give it to some other task. So you could actually improve clearly your utilization as well as the efficiency by releasing the processors that are not doing work anymore. Because if you look at this, this is a lagging task or lagging processors in the end, and all the processors can switch to some other task. Okay, so these are very fundamental, as I said. So let's go through Amdahl's law a little bit more, and I'll remind you the caveats of parallelism. These are my nice pictures, as you can see. My handwriting. Can you read this? It's not terrible, right? In the end, it's readable. You can train a neural network to read this better, probably. But anyway, so basically it's the same thing. This is so why do we have reality? So why do we have diminishing returns? Basically, as we said, the parallelizable part is not perfectly parallel, and the non-parallelizable part is essentially not parallel. Right? That's why you get these diminishing returns. As you keep adding processors, you don't keep getting linear speedup. You would get linear speedup if you don't have a non-parallelizable or serial part, and this basically holds. Basically, the parallelizable fraction is completely parallel. Okay, and as we discussed, this parallelizable part is so this is actually, I mean, maybe I'll go through this relatively quickly. TP is the time it takes to execute with P processors, and you can divide it like this. Amdahl's law divides like this. There's a serial part, 1 minus alpha. That remains the same as a single processor because it's executed on a single processor. Now these are all assumptions, of course, right? Because that may not be true because there's some data movement, data communication between parallel processors and single processor, but we're ignoring that here. And the parallel part gets divided by P compared to the execution time in a single processor. And if you rewrite this, you get this one. If you rewrite the speed up, you basically look at T1 divided by TP, and it looks like this. And that's again Amdahl's law, looked in a different way. And your speed up as P goes to infinity approaches this, 1 divided by 1 minus alpha, assuming this is completely parallel again. And that's the bottleneck for parallel speed up. Now you can actually draw a curve like this. I guess you could do it in Excel better, or any your favorite plotting, GNU plot or JGraph or whatever you use. Essentially, adding more processors gives less and less benefits if alpha is less than 1. It doesn't matter how much less it is. This is correct, right? Because this is asymptotic in the end. If your alpha is 1, then you get linear speed up, clearly. You keep getting the same benefit. Another way of looking at this is the benefit or speed up is small until alpha is really close to 1. And this is obvious also. And this is really what Amdahl illustrated in his paper. That's why you should read that paper. Basically saying that you really need to put a lot of effort to make the parallelizable portion really to make the parallelizable fraction really high. Otherwise, you don't get a lot of benefit. Otherwise, you might basically the paper is titled "The Validity of a Single Processor Approach to Achieving Large-Scale Computing Capabilities." Right. Otherwise, you might as well go with single processor. Okay, that's the idea. Okay, and we've already seen the slide. I'm not going to harp on it again. It's not just a serial bottleneck, but it's also these 3 fundamental reasons why parallel portion is not perfectly parallel. That leads to overheads, right? Synchronization, load imbalance, and resource sharing or contention. It's actually an Excel plot, so there's some homework that's done here as opposed to just drawing pictures. But I like this because it's very illustrative, right? This is parallel fraction of the program going from 0 to 100%. And this is speed up you get. And here we're looking at the curve for 10 processors, 100 processors, and 1,000 processors. And you can see that the speed up you get is kind of like a blip until you reach, let's say, 85%. So this is 10x over here. Clearly, you're getting 10x with 10 processors only if you reach 100%. And you're getting 10x with 100 processors when you actually reach whatever that is, 92%. Right? So your 92% of your program needs to be parallelized and perfectly parallel in the parallelized part for you to get that. And going from 100 processors to 1,000 processors doesn't make a huge difference. You still need to parallelize your program heavily, right? That's the idea over here. That's why Amdahl's law is so strong, as you can see. I think this is fascinating to see this way. Okay, well, clearly we have sequential bottlenecks, and people have tried to minimize the sequential bottlenecks, but they keep popping up. And right now we're not talking about the bottlenecks that we discussed in the parallel portion. The sequential bottlenecks are parts where you really have a single thread. And basically you have the single thread, it does something and then launches the tasks, and then you have a single thread that does something else, or maybe aggregates something, and then launches the task again. And a lot of parallel programs look like this way. And the main reason for the single thread is you have non-parallelizable operations on data, like non-parallelizable loop. If you cannot really parallelize a loop, what do? You execute on a single thread, right? Or you resort to some speculative parallelization mechanism that I mentioned earlier, which has a lot of overhead and which is not used in today's systems because of that. Like you have these recurrent data dependence on a previous loop iteration, for example. How do you parallelize this, right? Real life is actually much more complex than this. So there are clearly other causes as well. For example, a single thread prepares the data and spawns parallel tasks. We talked about the tasking. Like whenever you want to start tasks, somebody needs to keep the data structures, to keep track of the tasks, launch the tasks, and distribute the tasks. Now this could be somewhat parallelized, but this could also be serial. There are portions of this that are really serial. One example of this is from the paper, Accelerated Critical Section paper. It basically shows you that this is a dynamic tasking structure that's seen in a lot of dynamic tasking systems. But basically, if you look over here, this part is the serial part, A and E at the end. What do? Basically, you have a single thread that initializes some priority queue. This is a task queue. It spawns some threads, and for each thread, it does something over here. And then this is the parallel part, B over here, as you can see. And some part of parallel part is critical sections, as you can see. Like whenever you really want to get the task out of this task structure that was initialized over here, you do that. So you need to access shared data. And there's another critical section when you actually create new tasks. And then there's part of this over here. This is really the parallel portion that's outside the critical section. So this part is the only completely parallelizable part. But there are other overheads associated with it clearly, like load imbalance and resource contention. So that's subject to those overheads. In the end, the end-all serial part is here and here at the end, right? But for example, create solution. If this takes a really long time, then easily your parallel fraction can go down significantly, right? If this takes 10% of your time, going back over here, your parallelizable fraction is 90%, and you're really here. You're not there yet. That's why this is very strong. And in the end, it can easily take 10% of the time, right, depending on what you do. And on top of this, you have all of the other bottlenecks over here. Okay, so this is another example of the sequential bottleneck. Well, illustrated, A and E. If these take 10% of your time, you're 90% parallelizable. And inside over here, you have other idleness that's going on. And we already discussed bottlenecks in the parallel portion. Let me go over this relatively quickly again. Synchronization, operation manipulating shared data cannot be parallelized. And you've seen many examples of this. Tasks may need values from each other, as opposed to the example that we've seen where we ignored that. Right? And we already discussed this. Load imbalance. And load imbalance can happen because of imperfect parallelization and also microarchitectural effects. Right? You may think that you perfectly parallelize your program. Every task is doing exactly the same thing, but somehow microarchitecturally, one of them is being prioritized over others because your microarchitecture may not be fair. All of the issues that we've discussed earlier apply to this also. If you're not fair, for some reason, if you're prioritizing one processor over the other, even though somebody else perfectly parallelized their program, you may actually causing load imbalance, right, in the microarchitecture. So that's why that fairness is also important for parallel applications, actually. And resource contention, we already discussed this. Because you have limited resources and you don't replicate all the resources, you have contention in the resources, which could lead to load imbalance in the end. And which could also not lead to load imbalance, but basically lead to additional latency compared to when a task runs alone. Okay, I think we've discussed this over here. Any questions so far? So this is everything we've discussed, so I'm going to skip these. You can refer to the previous lecture, but I'm going to get to the end. So this is just a reminder that parallel portion, end-all law is very strong. You get a blip of performance improvement if your serial section is, until your parallel fraction is really, really high, more than 92%, let's say. But your parallel portion is not perfectly parallel also. So you can see now that multi-threaded programming is not easy, right? Okay, So, but of course people use parallel computers clearly, and there are cases where parallelism is very natural. They're embarrassingly parallel applications, right? Meaning, I don't think anyone has ever defined what this means, but the definition is probably your parallel portion is closer to 99% or so, or 100%, let's say. Clearly this exists in GPU use cases like multimedia, physical simulation, graphics, where you're really manipulating a lot of things, a lot of pixels, let's say, and you're doing it independently. You're not having a lot of communication. Clearly there are algorithms that communicate between different data pieces, and those lead to bottlenecks, but there are cases where you do independent operations on huge images, for example, right, or huge videos. Or large web servers and databases. This is another example where even though you have shared data structures, a lot of the operation is happening on non-shared parts potentially, right? There you get a lot of parallel. But really the difficult part is getting parallel programs work correctly, because it becomes actually harder when you get to over here. It becomes maybe easier if your parallel is very natural. But if it's kind of in between, now it becomes very difficult, right? You need to get your parallel programs to work correctly, and you need to optimize performance in the presence of all these bottlenecks. So in the end, much of parallel processing and multiprocessing is really about designing machines that can overcome these sequential and parallel bottlenecks to achieve higher performance and efficiency. And Cray 1 design is a very good example, right? As I said, that was the fastest parallel machine of its time, but it was also the fastest scalar machine of its time, because they knew that they couldn't beat other computers if they were not, if they didn't go fast in the serial bottleneck. Okay, this is one portion of it, but the other portion is also this, because in the end somebody's going to program these things, and making programmers' job easier in writing correct and high-performance parallel programs is really important. That's why a lot of effort in parallel processing and multiprocessing has been devoted to this. And we've already seen examples of this. That's why I'm going to tie to the earlier lectures. They're already on YouTube, actually. But basically, accelerated critical sections, bottleneck identification, scheduling. These are some modern examples. Utility-based acceleration. Essentially, handling bottlenecks efficiently are very good examples of this. Now, after the break, we're going to see different examples. We're not going to accelerate bottlenecks, but these are essentially looking at, can we actually make programmers' job easier by doing more at the hardware and the system and hardware-software co-design levels, such that, okay, maybe the programmer didn't perfectly parallelize their program, or naturally the program is not easy to perfectly parallelize, so we get all of these bottlenecks. But can we make life easier so that these bottlenecks are executed much, much faster? So this is really a performance/programmability problem. And as I said, you could punt on the programmer and say programmer didn't do the right thing, but that's not a good approach, right? You run to the performance correctness trade-off in that case. And we've already seen an example of the trade-off based on what you've done over here with limited time that you had for accelerating that program with a parallel computer. So in the next part of the lecture, we're going to talk about even more correctness issues, actually. Can we actually have a substrate? So these assume that that substrate already exists, and you optimize for performance and energy or whatever you're optimizing for. But there needs to be also a substrate that's really correct to begin with, and we're going to talk about those issues. So even getting the parallel computer architecture correct is not easy to begin with. Okay, any questions? Okay, so let's take a 15-minute break.